Good morning to all. Myself, Dr. Senappa. Now I will explain paper 501. In that paper, unit Astrophysics. In Astrophysics, now I will discuss about session 4. That is, it consists of the topics gravitational potential energy or self energy of a star based on the linear density model and statement and explanation of Varial Theorem. This is very important derivation. Gravitational potential energy of a star using linear density model. How we can derive this expression? It's very simple. We have to play with little mathematics. See, the work done in forming a star of a certain mass and radius from individual particles brought from infinity. Gravitational potential energy definition is it is the work done in forming a star of a certain mass and radius from individual particles brought from infinity. This is the definition of gravitational potential energy. Now, a vast cloud of hydrogen gas undergoing slow contraction due to gravitational attraction. See here, a cloud of hydrogen gas undergoing slow contraction due to gravitational attraction. Let a star of mass capital M and radius capital R be formed from a gas at infinite distance. Here in this figure, we can see a star of mass capital M and radius capital R. Consider the formation of this star as accumulation of small spherical shells. We can consider the formation of star in terms of small spherical shells. Let one such a shell be of mass dm, radius small r, thickness dr and density rho. See here in this diagram we can see that we have considered a small spherical shell of radius dr, mass dm, thickness dr and radius small r, density rho. Mass of this cell m is given by 4 pi r square rho of r dr. We know that in terms of density we can write the expression for mass as density is equal to mass by volume. Therefore mass is given by density into volume. Volume is given by 4 pi r square into dr. Density is rho. Let du be the gravitational potential energy acquired during the work done in bringing mass dm and add to the sphere of mass m of r. We have considered du be the gravitational potential energy acquired for this small spherical shell. Du is given by minus gm of r dm of r by small r. This is the expression for gravitational potential energy. We have applied this expression to write the gravitational potential energy for the small spherical shell. The total energy required to form the star of entire star that is of mass capital M and radius r is given by integration between the limit 0 to capital R and the same expression gm of r dm of r by small r. According to linear density model of a star, density rho subscript c is maximum at the core and decreases to 0 at the surface of a star. That means density is not uniform throughout the star. It is maximum at the core and decreases as we move away from the center to the surface, and it is 0 at the surface of a star. Therefore, radius at a distance r is given by rho c, that is density at the core, into 1 minus small r by capital R. Substituting the expression for rho of r in equation 1, we get dm of r is given by 4 pi r square rho c into 1 minus small r by capital R dr. See here we have substituted for rho of r in equation 1. Integrating this expression, we get u is equal to minus g into 4 pi rho c by 3 whole square, integrating between the limit 0 to r to the power of 4 minus 7r to the power of 5 by 4r plus 3r to the power of 6 by 4r square dr. By doing little mathematics, we can obtain the expression 6, and in that expression, if you substitute for rho c, that is density at the core, then we get the expression potential energy, gravitational potential energy U is equal to minus g by 3 into 16 pi square 3m by pi r cube whole square into 13 r to the power of 4 by 840. Simplifying this expression, we will get the expression U is equal to minus 26 gm square by 35r, which is approximately equal to minus 3 by 4 gm square by r. This is the expression for gravitational potential energy of a star. See, we can derive the expression by considering the definition of gravitational potential energy and write the expression for gravitational potential energy. We first you have to calculate the total energy required to form a small spherical shell by integrating between the limits 0 to r and applying linear density model, substituting the expression for density in that expression, and by doing a little mathematics we can derive the expression for potential energy of a gravitational star, that is minus 3 by 4 gm square by r. Now let us discuss Varial Theorem. Varial Theorem states that for any system of particles in equilibrium under the influence of force, thermal energy is equal to minus 1 by 2 times gravitational potential energy. Mathematically, we can state Varial Theorem as 2k plus u is equal to 0. K stands for thermal energy, u stands for gravitational potential energy. See, once again, I will explain. The theorem states that for any system of particles in equilibrium under the influence of force, thermal energy is equal to minus 1 by 2 times gravitational potential energy. We can write it as 2k plus u is equal to 0. Since u is negative for any bounded system, k is always positive. U is negative, K is always positive. When a body of fixed mass contracts, half of the energy released gravitationally would remain in the star and other half would be released as radiation. It also suggests that the thermal energy increases if potential energy becomes more negative. That means as thermal energy increases, potential energy decreases. The gases become hotter when compressed. How we can prove this Varial theorem? See, we can explain, we can prove this Varial theorem by considering a configuration of n particles, each of mass m, excreting gravitational attractive force on each other. Let particles be bound into a sphere of fixed radius smaller, then the moment of inertia of the system I would be constant. We have the expression for moment of inertia, that is I is equal to mr square. Moment of inertia about a center of sphere I is given by summation mr square, which is equal to m into summation r into r. We can write r square as r into r. Differentiating equation 1 with respect to t, we can write di by dt is equal to d by dt of summation mr square. That is, by differentiating this expression, we get 2m into summation r into dr by dt. We can, by differentiating the expression r square with respect to d by dt, we get r into dr by dt into 2. This is given by 2m into summation r into v dr by dt is velocity. Once again differentiating this equation, we can write d square by dt square is equal to 2m into summation d by dt of r into v. We have to differentiate this r into v by using the product rule, that is first function into differentiation of second and second into differentiation of first, and by doing little mathematics we can obtain this expression as 2 into summation r dot f plus 2 into summation mv square. Half into summation mv square is equal to k, the total kinetic energy, and summation r dot f is equal to u, total potential energy. Since I is constant, d square I by dt square is 0. Then from equation 3 we can write 0 is equal to 2u. See it. U is summation r dot f is represented by u, the total potential energy, and sum of summation mv square is represented as K, the total kinetic energy, it is given by 4 into K. Therefore, U plus 2K is equal to 0. This is known as Varial Theorem. See, we can derive the expression, we can prove Varial Theorem by considering the expression for moment of inertia, and by doing little mathematics. We can derive the expression for Varial Theorem. Hence, the theorem is proved.